Okay, I'm going to start section 11.6 here, which is called the absolute convergence ratio test and the root test. So those are the last couple of tests that we're going to look at here before we do a strategy for testing series. So there's a definition there. It says that the summation as n equals 1 to infinity of a sub n is called absolutely convergent if the summation going from 1 to infinity of the absolute value of a sub n is convergent. Okay? The summation as n equals 1 to infinity of a sub n is called conditionally convergent if it's convergent, but not absolutely convergent. Okay? And there's a note there saying that if the summation as n equals 1 to infinity of the absolute value of a sub n converges, then that's going to imply that the summation going from 1 to infinity of a sub n converges regularly. Okay? So if it's absolutely convergent, it will converge regularly. Okay? Let's take a look at some examples of this here. So in this first one, I got the summation as n equals 1 to infinity of negative 1 to the n divided by n to the fourth. Okay? This series will converge by using the alternating series test. So we just got done doing the alternating series test. Right? The limit as n approaches infinity of 1 over n to the fourth, that's 0. And the n plus first term is always going to be less than the nth term, okay? Because 1 divided by n plus 1 to the fourth is always going to be less than 1 divided by n to the fourth, because the denominator on 1 divided by 1 plus or n plus 1 to the fourth is going to be a bigger number than 1 divided by n to the fourth. Okay, so I know that this series is convergent by the alternating series test. I just said that. Now, the next question is it absolutely convergent? Okay, well, to be absolutely convergent, I got to throw absolute value bars around the sequence part. Okay, and I got the summation as n equals 1 to infinity of the absolute value of negative 1 to the n divided by n to the fourth. Okay? Well, n is already a positive number. You're going from 1 to infinity, right? So n to the fourth is going to be a positive number. And negative 1 to the n, that's always going to be 1, because in the numerator I'm going to get 1 or negative 1 each time. So with the absolute value bars on that, I'm going to get 1 each time. Okay? So this ends up being the summation as n equals 1 to infinity of 1 divided by n to the fourth. And this is a p-series. P is 4, which is bigger than 1, so it's convergent. Okay? Therefore, the original series is called absolutely convergent because it converged regularly by the alternating series test. It also converged when I throw absolute value bars around the sequence part. Okay? Let's try another one here. So in this next example, suppose that we have the summation as n equals 1 to infinity of negative 1 to the n plus 1 divided by n. So this is the alternating harmonic series. That was the first example that I showed you in section 11.5, and that was a convergent series. It converged because the limit as n approaches infinity of 1 over n, that's 0. And 1 over n plus 1 is always going to be less than 1 over n when you're on the interval 1 to infinity. Okay, so that one converged. Now, the regular harmonic series that's divergent, we're not talking about a regular harmonic series with that negative 1 to the n plus 1. Okay, so I know that I've got a convergent series here. Now, the next question is it absolutely convergent? Okay, so let's throw absolute value bars around the sequence part. And I got the sum as n equals 1 to infinity of the absolute value of negative 1 to the n plus 1 divided by n. N, again, is already a positive number, so I don't need absolute value bars down there. And negative 1 to the n plus 1 is always going to be 1 or negative 1. So when I have absolute value bars on that, I'm always going to have 1 up top. Okay, and that means that I'll have the summation as n equals 1 to infinity of 1 over n, which is the harmonic series. And I know that diverges. Right? We saw that in section 11.2. So it converged by using the alternating harmonic series test. And when I throw absolute value bars around the sequence part, now I've got a divergent series. So I'd say that the original series here is called conditionally convergent. Okay, it's convergent, but not absolutely convergent. Okay. Let's try another one here. So what if I have the summation as n equals 1 to infinity of sine of 4n divided by 4 to the n power? Okay, so I want to know, is that absolutely convergent or conditionally convergent or divergent? Okay, well, let's see. If I throw on absolute value bars around the sequence part, then now again, why I'm doing that? So if the summation as n equals 1 to infinity of the absolute value of a sub n converges, then I know that the summation as n equals 1 to infinity of a sub n converges. Okay, so I basically I'd like to know, is this series absolutely convergent, conditionally convergent, or divergent? Okay, so if I throw on absolute value bars on the sequence part, 4 to the n power, that's always going to be a positive number because I'm on the interval 1 to infinity. So I can lose the absolute value bars there in the denominator. Now sine of 4n, that's sometimes a negative. So I'd want to keep the absolute value bars on the numerator part. And I've got the summation as n equals 1 to infinity of the absolute value of sine of 4n divided by 4 to the n. Okay, now the next thing I'm going to do is I'm going to use a comparison test here. So the absolute value of sine of 4n, that is always going to be a number that is less than or equal to 1, right? 1 is the biggest value that you can have for when you're computing sine of a number. Okay, so I can say that's going to happen for all n, right? Now, if I divide both sides of this inequality here by 4 to the n power, then I got the absolute value of sine of 4n divided by 4 to the n, which is less than or equal to 1 divided by 4 to the n. And by the way, I can keep the inequality sign facing the same way, facing towards the right, because 4 to the n is a positive number. If 4 to the n was a negative, then I need to flip the sign there. Okay, I'm not doing that though. Now, 1 divided by 4 to the n, that's the same as 1/4 to the n. And the summation as n equals 1 to infinity of 1/4 to the n, that's a geometric series. And the r value is 1/4. The a value would be 1, right? And now actually, to find out what this series converges to, I'd have to pull out a 1/4, so it'd be 1/4 times 1/4 to the n minus 1, and then I could use the formula. Now, it's not necessary to do that, though, because all we care about is, does the series converge or diverge? Well, it converges, okay? Because r is, less than 1 and bigger than -1. So now I'm comparing this term by term with things on the right and things on the left, and when I add up all these numbers on the right, I get a grand total that's a finite number. So if I'm adding up smaller results on the left, I know I'm going to have a finite number. Okay, so the summation as n equals 1 to infinity of the absolute value of sine of 4n divided by 4n, that converges also. Okay, we're using a comparison test there. And the summation as n equals 1 to infinity of the absolute value of sine of 4n divided by 4n, that is equal to the summation as n equals 1 to infinity of the absolute value of sine of 4n divided by 4n. Okay, so I'm saying that series converges. Okay, and so the original series here, I can call that absolutely convergent. Okay, so the sum as n equals 1 to infinity of sine of 4n divided by 4n, that's absolutely convergent. Okay? And, you know, so in some of these problems, like it's going to be, you know, easier for us to just see does the series converge absolutely or not? Okay, and then go from there. So that's what we're doing in this problem. Okay. Now, the next thing that we're going to talk about is the ratio test. The ratio test is super, super important. We're going to be doing lots of things with the ratio test here over the next 3 sections. Okay? You got to know that one. So the ratio test is one of 3 things is going to happen. If the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is a sequence, if that's equal to L, and L is some number that's less than 1, okay, then the series given by the sum as n equals 1 to infinity of a sub n, that's absolutely convergent, and therefore it converges regularly. Okay? Item 2 says that if the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is equal to L, which is greater than 1, or if L is infinity, then the summation as n equals 1 to infinity of a sub n is divergent. Okay? And then item 3, if the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is equal to 1, then that means that the test fails. Okay, and really that the test gives no information. Okay, that is, no conclusion can be drawn about the convergence or divergence of the summation as n equals 1 to infinity of a sub n. Okay, and so we got to find out, using a different test, does the series converge or diverge? Okay, now don't get this confused with the limit comparison test. The limit comparison test, that's a totally different test, right? And so I got to find a comparison sequence, and I'm looking at the limit as n approaches infinity of a sub n divided by b sub n, and I just need to know, is that greater than 0? That has nothing to do with anything I'm talking about with the ratio test. Okay, so don't confuse those 2 tests. Some students do that. Okay. All right, we'll look at some examples of where we're using the ratio test here next, okay, and then I'll talk about the root test also, okay? So we'll do that in the next video.